Okay. Let's see. Insert picture. Okay. Okay. We've got my page. Please. Dun, dun, dun. Very nice. See, this I wasn't 18. I was like, I was about 45 or something. But anyways, it said Alan Turing was 20. I think he's older than that in this picture. So maybe it has got this bias where it's trying to flatter you or something. Let me try something. Insert picture. Okay, let's there. This is more recent, definitely. Okay. This was 10 years ago, right? So that should be 4. Okay. That's correct. No, I was younger than that. Never mind. Okay, so it's not perfect. Okay. Okay, very good. Now, I noticed, by the way, that I think some of you that have problem with the midterm probably kind of like maybe you were nervous with the coding part. The best thing to do, okay? For example, for sure, classify is going to be on the exam, right? Classify is going to be on the exam. So to study, not only should you look at the book, you should look at this page, this built-in place page, classify, right? Go through all the example, okay? All the, there's a lot of example and explanation, okay? Go through that, okay? Anyway. Okay, so let's go. So Alan Turing, this may have been accurate because he died very young. He was like 51 or something. But this picture would have been probably after the war, so it would have been 40-ish something. This, yeah, I think probably I was 40. Yeah, maybe 48. Don't remember. Okay, so, okay, let's go. Now, I mentioned that your project should be from, a big data set. A good example would be, okay, for example, I go to this thing, okay, let's go to the first one. I'm interested in agriculture, blah, blah, there's agriculture. I want to look at just the first one, anthropogenic biome. I don't know what that means. So that's, okay, so time series. So presumably this is about effect of man. So this gives example of how you work through. So what's cool about this data set, and if you go to GitHub or Kaggle for data set, it's going to be explanation on the data, okay? Because most people are already fairly good with data science, they'll know what to do, basically. You just need to point to where the data is, example file, give a little bit about what the data type is. Whereas here, in the data repository, it gives you an example. It gives you an example of what? Of how to work with it, right? For example, this thing is a data that has to do with a human footprint in different part of the world. So it gives you an example of, okay, the position, give a geoposition of this. So this is what happened. So, something like a coastline, victim. I don't know what the example does here, but it certainly show what happened when human footprint in East Africa, in Europe, something. Okay, so it's not just giving you the data. That's what I'm trying to say. Okay, it's giving you a heads up on how you would work with it. California crop mapping. This one is, let's see what it looks like. I think it's just a table. This one is like an Excel. Okay, so fine, not that interesting, but still, yeah, it does have. So it because it does have location. Okay, you can do group by crops. You can do county. I think this is this is California counties, and it gives you a sort of like a how much, you know. So just looking at this alone, you can almost see the visualization part of your project already done for you, right? For this data, it makes sense to look at annual rainfall per county in California, whatever, right? So obviously, a lot of this data will be you know, North America centric. Okay. So oil and protein in corn. Okay, so let's say we go to okay, health. A lot of you guys in health, right? So health. Maybe you are interested in a list of epidemics. Fine. Okay. So this gives you a timeline of epidemics. That's hospital resource use projection. Fine. So this United States. So this will be more time series based. Okay. So all this. So what I want you to do, before I forget, for homework today is number one, you know, this classifier, classify, right? And this is the built-in one. For each of those, there's only about 10 of them, okay? Give an example, okay? So for example, something like, what is this? Facial gender, okay? Then obviously, now this, the first time again, it's gonna, and then you put in your picture. Better give mail. I'm gonna be really mad and cancel. Okay, good. Not too bad. Okay, so what else is there? It's about human being, sentiment, country fact, Facebook, facial age, facial gender. Yeah, maybe facial age. So this one here is probably not going to be as good. Okay, so the first one is, okay, first one is new example. Okay, you can put in your face. Don't use my face. Facial age, that's a built-in one, right? This one should not be as good. Should not, I stress, should not be as good as when you go to the net repository and look at age. Where's the age? Okay, so there are actually quite a few actually. Oh no, that's image. Okay, so there's a age estimation, version 1, version 2, caps. Okay, so something like this. So you would say, okay, let's compare the silly one, the simple one, with the more advanced one, right? So yeah, in my case, that's correct. When I took this picture, this would have been, you know, 10 years ago. I'm turning 56 Thursday. So this was 10 years ago. So this is not correct, right? This is not correct. This is better. Okay. But if you notice, the first time you load it, by the way, use this function, timing. Okay. The function timing, when you put it around anything, it's going to perform the calculation, but it's going to give you the number of seconds it took your machine to do that. Okay. Now, it varies. If you use a fast computer, it's so what I want you to do is for homework, okay, for all this thing, meaning classify, all this built-in, right? There's like 10 of them, I think. Okay. Find an example. Okay. Maybe don't do profanity. I don't want you to turn, well, that's fine. You can turn in profanity. Okay. But be gentle. Don't be that rude. Okay. So profanity. Okay. So classify as fudge. See if that's okay. Nah, okay. So that's okay. That's a good word. You can use that, right? But if you add the F, it should be positive. You see what I mean, right? Okay, good. So again, now if there is a profanity in here, if there's I don't think there is. Maybe there is profanity. Nope, there isn't. If there is, take an example from this page. Okay, again, the age is a good example, and compare and see which one is more accurate. Okay, so you should have like 10, 20 lines or something. So like this one, if you don't want to use your picture, you can use Alan Turing. So there's this one on age. There's probably one on sex in here as well. Sex detection, or maybe not. Okay. Now, there aren't that many here. A lot of it will be like with language, which we're not using yet. Okay. Predict. Huh. Predict name age. Let me see what that is. Oh, it uses text. So 56, intermediate. 95 years old. That's not very good, is it? I don't know what that is. Okay. Or maybe the other way around, sorry. Predict name age may be something like old, yeah, young. Maybe very young. Okay, like I said, all this kind of like quotation built in are not very good. Okay, so the homework you have today is to do basically this and this, right? So for example, of age prediction, use this thing, and also there's one for here. This one is okay. There's image and all kind of stuff. Okay, right. So now that's the first half. Took a bit long. Now I'm gonna pretend that you are a novice data scientist. Okay, what I mean is that you are not expert in data science, but because of the problem you have, you're not trying to identify cats from dog, which is already built in, right? So if you have something that's already done here, I can guarantee that you're not going to do a better job. Okay, so for the task out here, okay, so the task could be facial recognition, predict the next word, sentiment analysis, all those tasks. Based on those data, you're not going to do a better job because these are done by professional academics and researchers who spend months on it. Each one of these probably costs millions of dollars in man hours just to produce, right? So you're not going to do better than this guy. You're not going to do better than this guy. But let's say in your problem, you have your own data set, right? So it's better to build from scratch. It's better to build from scratch. Okay. How would you do that? Well, I'm going to take you through. And again, it's going to be based on example data. So we take, so this would start from the book section. What section is this? Guys, remember? Where's the book? There. So start from section. So we learned about this last week. There. Procedure. Okay. Procedure. Okay. So you are going to train a machine learner. Okay. You can train a machine learner. First thing first, you have to divide your data into at least two sets. One is a training, one's a test. On the exam, I will ask you to explain validation set as well. Remember, validation set is like pretend test set that you give to algorithm so it knows when it's overfitting, right? But that's only one way of preventing overfitting, this validation set. But the most general form is train, test. And that mimics how you work in real life. Train is how you build model based on the data. Test is how well the model does on the data set it has not seen. It has not seen. Okay, it has not seen. Now, first thing, you have to separate training versus testing set. I'm gonna draw, I'm not gonna go over there because it's gonna waste too much time, but let's go paint. Okay. Okay. So this is your data. Your data. This is your data. Okay. What you're going to do is this. Train based on this, and then test based on that. Right? So this could be like 30%, 20%, or 10%. Okay? Does that make sense? Right? Now, does it have to be contiguous? That's a good question. Can I sample randomly 70%, put it one side, 30 random percent to the other side? Can we do that? Well, it depends. Is there a time series structure? Right? If it's a time series structure, you want your data, the testing to be like contiguous period. Like this would be like the last 3 months, and that's the previous 9 months. So you train on the previous 9 months, test on the last 3 months, right? So if this is a time series, but if this represents all your clients, can somebody check the air conditioner? It's so hot. If this represents 100% of your client, and there's no time series, it's not like a early client, late client, just all clients, right? And this just happened to be listed randomly, okay? Then this 70, 30%, it just means random 30%, random 70%. Okay? Now, let me tell you something. You might, when I said, okay, let's train the first 9 months and test the last 3 months. Some of you might ask, hey, why not train the last 9 months and test the first 3 months? Can we do that? Yes, we can. So we can do this. Instead of this, we can do this. Train and test. Okay. While we're there, how about this? How about train, test? How about train, test? See that? So you will notice that they take turn being the testing data. Okay. This kind of thing, by the way, is called n-fold validation. In this case, it's 4-fold validation because you take 1, 2, 3, and 4, right? So that's more advanced, more industry practice. Okay, but for this, for our job, for our purpose, let's make it simple. You have a train, and you have a test. Now, how would you do that? Let's say my data is, okay, I'm gonna make this up. Okay, you should type as well. So let's new page. Okay, so let's do this. Array, table. Okay, X, I, Y, I, 5. This array. Oh, sorry, the table is good. Hold on. Does this work? Okay. Let's do this. Array X 5. Let's make it 120, 1,234. Okay. So that's that. Okay. And then I'm just going to make this array Y 1, 2, 3, 4. Okay. And I'm going to call this thread. Okay. You guys remember the thread function? Okay. So basically it's a pair of X1 to Y1, X2 to Y2. Okay. So assume this is my data. Okay. My data. Okay. It's my data. Okay. Now, one of the easiest way to do this, okay, is, tell you what, let me do that. Let me give you a real data set. So let's okay, we can do this. We can do this. Okay. So this is a data, right? It's a data. So let's say you got this data set. You need to know how many length data. It's 123, right? So let's say you want to separate. Let's use a 80-20% split. Okay. 80-20% split. How would you do that? You would do this. My train data, my test data is equal to take drop, okay, and data, and I think you have to put the portion first. Hold on, let me check the. Yeah, that's right. Okay, so what you do is you say something like, I don't know, 0.7 times length of data. That's what you want to do. Okay. Now, if you did this, it's not going to work. It's not going to work. Why do you think this doesn't work? Because 0.7 times this is, it's not an integer, right? So what we have to do is do something like floor. Okay, just round it down. Just round it down. Now you can. Okay. So now, if you did this, length train, oops, test is going to be that, right? Okay, so this is this I make this up. Don't worry about it, right? I'm just making 1,234x and 1,234y, and I just make them point to each other, right? Or I can do something, you know, so it could be like x1, x2 if you want, x1. Okay. Now the length is this. I want to take 70% as my train. So it's 70% times the length, right? And then you throw it to make an integer. So that comes to this. Okay. So this is about 70%. Yeah, 69%. Okay. Close enough, right? So that's what you would do. You have a train data and test data. Okay. Okay. Forget about info validation. Okay. So this is how you would do in general. Now let's go back to our example. Okay. So yeah, I did this already in example as well in the book. Okay. So I have an example like x1, x2 to y1. I didn't know why I had to. So I take example 0.7 and floor. Okay. All right. Now, okay, for validation, don't worry about it. I'm skipping that. Okay. The idea is that in order to work on this, everything has to be in a X point to Y format. Okay. Now, because I'm using example data, okay, in fact, I'm using machine learning example data of Boston Home. Okay, it's already in that format. Not only is it that format, I think it's already partitioned into training and test set. There it is. Okay, so I don't have to do take drop here. Okay, here I have to do my take drop. Okay, take 70% and drop it. This case, it's already separated into training data and test data. Okay, so let's do that. So this is my training test data. Okay, now let's see what test data looks like. See? Can you see that? What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 number. Predict one number. Okay, this is some kind of house price, I think in thousand or million. I don't know. I don't remember. Okay, so 13 number predict one number. 13 number predicts one number. Okay, now how big is this? 168. And train. Okay, so the example has about 300 houses and tests on about 130 houses. Okay, so that's one data set. That's for prediction. Now let's look at another example. Another example is also machine learning, but this one I'm predicting the flower. Okay, so the flower, again, I'm doing this same as before, except now I do, let's look at the classifier data train. Yes. 1, 2, 3, 4 number predicts this. Okay. So they're actually Setosa, versicolor, and Virginica. Right? And how many of them? 45. It's very even smaller. 105 for train. So very tiny data, like I said. Okay, this is all baby set. Okay. So now I've got two problems. One is to predict house price using 13 numbers. One is to classify flower types using 4 numbers. Okay. The detail of what it is, you can look at from reading description or something. Okay. But now I don't care. So first thing, I get the data, put into X point to Y, and then I partition into train versus test. Because this one is an example data, it's already done for you. Fine, so you have to do that. Second, so now I'm gonna build the model. Okay, this is what I mean by you have to build this yourself because in your problem, it's not available. Okay, it's not in this page. Okay, let's say you want to predict, I don't know, happiness of a cat or something like that. And you can't find happiness of a cat predictor here. So you have to build your own cat happiness predictor. Okay, that's what you have to do here. Okay, so what you have to do is use the function predict and the data. What data do you put in? Training data. Okay, now I'm doing 2 lines because I want to compare 2 ways. One way is my predictor is equal to predict this. The other one, I say my predictor has to be neural network. Okay, has to be built in a network. So even your job as a novice data scientist, you can use classify without specifying method. Same thing, you can also use predict. Okay, now I happen to use both predict and so You guys okay with that, right? I'm doing both prediction and classification. I'm doing two problems at the same time. Okay. Or would you want me to do prediction all the way and then classification all the way? Now let's do what each, right? You guys handle that, huh? Yeah. Okay. So use predict or classify without specifying, or B, use predict or classify with specify method. Okay. So this example here, I want you to type exactly like I did, right? Predictor equal to predict data. Okay, what's this data? This data is basically this guy. Example data, Fisher Iris. Okay. So this is sorry, Boston house price. So I'm gonna do this. Okay, I'm gonna do this. Watch what should happen. Okay. Now I'm gonna train two model for the prediction. It's doing that right now. It takes 1 second. And the first model is called a random forest. The second one is neural network. It takes a little bit longer, 9 seconds, 10 seconds. Now this is minimizing in real time. It's minimizing the classification. So 5 seconds, 17 seconds, 18 seconds, 19 seconds, 20, 21, 22, 23, 24, okay? The reason I gave you two examples is I want to show you that potentially the better model will take longer. And this is always the case. And that's, you know, this GPT 3.5, it has so many parameters. It takes the most advanced company in the world months to do what we're doing now, okay? So the first one takes 0.5, okay, so it takes longer. The first one happened to be random forest. The second one is a neural network, so it's a neural network. Now, so I'm training the prediction. This is predicting house price. I'm also going to do classification. Okay, I'm going to do classify flowers. Again, I have a classifier, classify, data train. Classify here, in this case, my choice, I happen to use DT. Don't ask me why I like DT. This is decision tree. So that's my method, decision tree. Okay. In this case, the method I choose actually runs shorter time. The one that mathematics I choose is logistic regression. The one that I choose is decision tree. That's it. Okay. It's done. So now you have this guy to classify. And you have this guy to predict house price. Okay. And again, it shows you the number of sample it used. It used 338 houses to train and 105 flowers to train. Okay. It's a bit hard to see. Just, yeah, this is from the book. So exactly look at the book. You don't have to look here. Now, you have to then test, right? So you build this, use predictor. Use classifier measurement. Or obviously, what's the other one? Predictor measurement, I think. Predictor, TOR, I think. Yeah, TOR, okay? So this is my predictor measurement, okay? When I create this object, it's gonna measure all the measurement. Okay, how many ways can you tell whether or not the supervised learning model is working? It tests all that. However, it's just going to show you the most popular one. Okay, and the most popular one for predictor would be here. Okay, so now this is just putting in table. You can type this in individual line. Okay, These are the popular predictor. In other words, to predict the house price, these are the items. Now, when you measure the performance, what is the performance? What data set should you test it on? Training or testing? When you give the result to your client, you have to give the testing, right? Because that's only fair. Now, as a data scientist, you also want to know how well your model does. So you test both. I always do that. I test in sample, training set. I test out of sample, testing set. So you will see why I have this on train and test. Train and test. However, if I give this one, the left-hand side to my client, I would be cheating, right? Right? That's cheating. That's dishonest. Giving the testing performance on the data you use to train the model. That's dishonest. I do it here because I want to see how it's doing. Okay. Now, but essentially the number that you have to give is this. Okay. So what's, okay, this is just a summary. It's the name random forest, standard deviation, 4.65. So I think unit of, I don't know, $1 million or whatever it is. Standard deviation based on R square. You guys are familiar with the R square, right? R square of 0.7. The in sample is obviously higher, it's 0.85, but that's not realistic because, you know, that's the data you see. So this is the one you should report. Mean cross entropy, that's also, you know, valid for machine learning class. You don't have to worry about that. Single evaluation time, that's just a microsecond per sample. Now, this one is the one you would put in your PowerPoint, because this is a predicted value, this is an actual value. So if the predicted and actual value are the same, you would expect them to be on the 45-degree line, right? So if the actual is $20,000 and you predicted $24,000, so you overpredict. If it's $20,000 and you predict $18,000, you underpredict, right? And if you take the real versus the actual versus predicted, minus them square, that's mean square error. That's this guy. And take standard deviation. Okay. So basically, average distance is about $4,000 error. Okay. So that makes sense, right? The output is a number. So you compare number with number. So you have 45-degree lines. Okay. Now, what if the output you decide is not a number, but it's a class? It's name of the flower. You also have 45-degree line, except it looks like this. Okay. So I'm going to do predict the measurement. Before I go to the flower, this is for the random forest, right? This is the one the Mathematica picks. This is the one that I picked. I want neural network. Okay, and see what I got. Neural network, the in sample R square is even better. Now, most of the time, neural network will work better, but you can see why Mathematica chose random forest, because random forest is much quicker. There's some other criteria you can read here. I'll show you. Okay, so that is right. Likewise, I'm going to test for. Well, let's not finish yet. So these are the most important number, right? R square, standard deviation. I'm not sure what standard deviation baseline means. Okay. Mean cross entropy, that's also important, but don't have to go into it right now. And this kind of like actual versus predicted product, that's the most important. But like I said, when you build this performance predictor measurement, it measures everything. In fact, I take this thing and I put the word properties. Where's the word properties? There it is. Okay. You will see that not only does it measure, what was it before? Mean standard deviation, mean cross entropy, right? R square, right? And what was that plot? That plot is called is it Irish plot? Comparison plot. Yeah, I think it's just comparison plot. So if I say predictor performance, predict that data. Get this right. So that's comparison plot. That's comparison plot is this guy R square, R square, R square, R square is this guy, and mean cross entropy, that's this guy. But obviously it has a bunch of other things. So I can do residual plot if I like. I can do residual plot. Okay, this is also very popular, but not as popular. Let's see, more certain example. Most certain example is the one that, you know, the prediction is more sure. It's this sample, predict 24. Okay, so you can get all kind of performance statistics. So by doing this one line, it measure everything. Okay, it's not like in a programming language where you have to ask it for individual measurement. This one say create all the measurement, but you don't have to report it if you think it's too much. Okay, it's too detailed. So it gives you the top level. Again, this is very nice way of working. So this is based on what most people think is important. But let's see what else is interesting. If you want to, you can dig deeper and you look into residual histogram. That's okay. Now this one I'm going to be using later. Okay, sharp plot, sharp value. Okay, so keep that in mind. Keep that in mind. Keep that in mind. Okay, right now. So let's look at this one. Let's go to the flower prediction. Likewise, I have a cloud performance measurement. I call it class. This is a function, classify measurement. So based on Mathematica's logistic regression. Now the performance statistic will be slightly different. Okay, there'll be now accuracy number instead. There's no R square here. And this is how you compare the 45-degree line, except this 45 degrees go this way. So this is actual versus predicted. So if the actual is setosa, and there are 15 of them, the model predicts setosa 15% of the time. Sorry, all 15, correct. So obviously this is correct, right? Of all the versicolor, and there are 15 of them, the model predicted 14 of them, right? One of them is wrong. See, that's an error. But you can see, out of this 45 testing, how many error did it get wrong? Basically, how many off diagonal? One. That's pretty good. And that's why the accuracy value is 97.8%. Okay. Now, this is the decision tree. Decision tree is not, it's only, yeah, it's just as good, basically. It's no difference. Okay, got two error. Can I see that? Now, likewise, there are other things that you can check. So, here's this one. You can check for false positive example. So let's go to a classifier DT performance test. And this one is wrong. Okay. So So these are the falsely identified. And so you can get the example F. So in this, there are this thing called F1 score. There is this thing called precision. There's this thing. It's a lot more. I think this is a lot more. There's ROC curve. Now, ROC curve is one of the most important thing. In fact, I'm surprised it's not put here, but okay. To me, it's almost like you would put ROC curve all the time, but Mathematica doesn't think so. It thinks gives you the confusion matrix is good enough. Okay, so this is called confusion matrix. This thing is this guy, confusion matrix plot. Okay, but I also think that this thing is also good. But anybody knows what ROC curve is? Okay. Yeah, I think it's good. Let me do this. Let me cheat a little bit. Let me have you read about ROC. Okay. Basically, okay. Now this one is a little bit hard to say because you have 3 classes. Okay. But you can imagine, right? For setosa, okay? Meaning the flower is setosa. Okay. What are the 4 situations? 4 situation is it's not setosa. The model say it's not setosa. Okay, that's one situation. So that's correct, right? That's true, true negative. Positive meaning yes. If it's setosa, meaning positive, and the model say positive, right? Then it's good. So it is true positive, right? Okay, what are the other 2 situations, guys? Okay. It could be setosa, but the model doesn't say it is. It is a false negative. It say no, it's not setosa, but it said wrong. How about it's not setosa? The model say yes, it is. So it say positive, but it's false. So it's false positive, right? Now the reason I hesitate is because yeah, let's do that. Let's not hesitate. Let's go to the screen. It's too important. Okay, I'm gonna go to the screen. But anyway, the thing you have to do is what's called ROC curve. Okay. And there's this thing called positive, false positive, and this recall. Okay. Now, yeah. Share. Okay. I think because this is going to take a bit of time, we won't start unsupervised learning today. Okay. Okay. You guys remember okay, this callback. This is also a callback in statistics. Huh? Yeah. Yeah. Okay. Remember in statistics, right? And you're asking the question, where, right? Okay. So what you want to do is maybe you have a histogram and you do a plot, right? Right. Now, in If you want to say, what is this? That's called estimation. Yeah, estimation. So let's say estimate mean of the data. Okay, that's called estimation, right? It tells you where the data is. Now, the opposite of mean is testing. It's called hypothesis testing. So let's say, okay, let's say this is something bad. Okay, the value is something bad, like amount of poison contaminant released in the water. Okay, right? So regulation is that this average pollutant is less than or equal to 0.07. Don't know what unit is, okay? 0.07 milligram, whatever, I don't care, okay? Right? So what you do is you test whether or not this is the case, okay? Now, let's say this is the case, okay? It's a factory, and this is pollutant. Okay? And this is 0.7, right? Okay. And I come and collect data, and I get this point, get this point, I get this point, I get this point, I get this point. Is that a problem? Is that a problem? No. You're below, right? One out of 7 days, you get that. My question to you is that a problem? This is where statistical evidence is judged. If intuitively, a whole bunch of time is below 7, but there's only one time it's above 7. It could be just that day, right? Because after all, your regulation is not every day. Your regulation is on average. You must not pollute more than 0.07. That's the regulation. The regulation is not every day. Okay, this is not a speed limit. Okay, so if that were the case, something like this, would you be okay? Would you give this guy a benefit of a doubt, or would you throw him in jail? You would give him benefit of a doubt, right? Right? Statistical inference, in fact, this is what the career of your friends in statistics does, is to tell whether or not this situation is consistent with that. Now, how can this be wrong? How can this be wrong? Well, what if for the next 500 days it's always here? You're probably going to think that's not right, right? One day, okay, it's a fluke. 2 days, maybe it's a bad 2 days. But if for the next 100 days you get everything higher than 0.07, would you still give that guy benefit of a doubt? No. Okay. Or also one day, but instead of here, way out here. Well, that's also scary, right? It's that weight of evidence. Okay. So what happened is, and to a lot of you, this is probably a review. The claim, okay, let's say I know how widespread it is. I'm just claiming that this is 0.7. Mu naught is equal to this. Alternative, if it's smaller, I don't care. I want to japit. I want to catch this guy in the act. So mu attorney or alternative, right? General alternative is greater than 0.7. Okay, this is called null hypothesis. Sometimes you will see the word HO. This is called HA. Okay. And in which case, you don't have to write the word here. That's right. Yeah. Just put the O and A here. Okay. Right. Now, here's an idea. Okay. Here's an idea. You can be wrong two ways. Okay. You can be wrong in two ways. One, less than, I'm not going to add. Okay. 0.07. Okay. But then you say guilty or not. Okay. Or you can say, oh, this is reality. This is what your model say. You can say guilty or not. Right? Okay. What is the correct course of action? The correct is, if it's this, then you say it's not guilty. If it's greater, then you say it's guilty. Okay? Right? What's the wrong? It's this one is okay, but you say it's guilty. Another way you're wrong, the prosecutor, it's guilty, but you say it's not guilty. Okay? So what are the four situations? Innocent person, not jail. Let's fine or jail, same thing, okay? Not punish. Guilty person, jail. This one, innocent person, jail. This is false positive. Positive in this case means yes, this guy is guilty. Okay? So it's not positive in a nice way. False positive. Yes, this guy is guilty. But no, that's not true. How about this? False negative. He's guilty. I say not. Okay? So there can only be four. There are two ways to be right and two ways to be wrong. Okay. Now, you say this is guilty. Okay, let's use the word guilty. Okay, guilty. Not. Now, the prediction is on which axis? I keep forgetting. By convention, I think you put it there. Nah. Okay. Let's say this is actual, guilty, and you say this. This is what you say. This is actual. This is actual. This is what you say. Okay. So here it is called true positive. Okay. This is called true negative. Okay. True positive and true negative. And this one is false. False what? Oh, let's just false. False what? False negative, because that's what you say. This one, false positive. Okay. My question to you is, what do you want to do? You want to maximize this guy, and you want to minimize this guy, Okay, that's common sense, right? That's common sense. Okay, so if I, instead of having this, I actually have number. I actually have the number of confusion table. What's my accuracy ratio? It's number of blue divided by number of blue and red. That's accuracy. However, in real life, okay, two situations. Okay, let me ask you two situations. Okay, what happened is this. Let's say you measure the contamination, right? And okay, you say, I'm gonna say, if I take an average and it's to the right of this, I'm gonna say the person is guilty. Is that fair? Okay, so let's say this is 0.7. Okay, 0.07. I take an average and I plot. Again, like picture before, except this time I'm going to show just the average. If the average is here, are you okay? Yes. If the average is here, my question is, are you okay? Not just 1 point, the whole average. Is it possible that this person is completely honest? In other words, this is how he emits pollutant. Okay? But for some reason, there's kind of like a positive probability that for the data set that you will collect, so this is a distribution of the sample. Okay? There's a subtle difference in definition, but this is how the sample of 10 days average should be. Okay, if you collect data for 10 days, the average should be like this. Okay, and yes, because this guy is operating by the law, right? On average, he's below, right? But is it possible that even though his true mean is below 0.07, if you collect sample for 10 days, you get something higher? Can you do that? Is it possible? Yes, it is possible. Just bad luck, right? Bad luck, right? Does that make sense? So my question is, how much should you give this hard deadline? Okay. Certainly it's not going to be below 0.7, right? Certainly it's going to be a little bit higher so that it allows for this, right? But you cannot go all the way down, right? Because at some point you have to say it's guilty. So at some point you have to set this line. Set this line. Now, if you look carefully, this is the probability of false positive. Probability of false positive. In other words, he's okay. Okay. But because you're cut off, remember, this is not about the claim. This is about the cutoff. If I say, okay, I don't care, I'm going to give you benefit of a doubt. So if I collect data water sample and it comes out 0.071, it's okay. But if it comes out 0.079, I'm going to fine you. Okay. So this is my hard cutoff. But here's the thing though. If this were the case, that's a probability of false positive, right? So what do? Well, you just move it over there, right? So that it's smaller. You can't. You know why? This guy could also be guilty. It's a little bit hard. It's a bit hard to draw. If this guy is guilty and I set my cutoff here, this area here becomes probability of false negative. Okay, you don't have to replicate this picture in the exam or anything, but all you have to remember is that the more stringent you are, the higher probability of false positive. So in other words, false positive and false negative cannot be minimized together, right? Right? And that's real life problem. If you are going to say, I'm not going to trust anyone. I'm one of those judge, right? Anytime anybody comes to my court, I'm going to say he's guilty. Okay, I'm that kind of judge. Anybody comes to my court, I'm going to say guilty, 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 guilty. I will have 0 false negative because I have no negative. But I have a lot of false positive, right? On the other hand, if I'm a super lenient judge, everybody comes to my court and I say, not guilty, not guilty, not guilty, not guilty, go home lah. I'm going to have 0 false positive, but I'm going to have a whole bunch of false negative, right? So if I move this thing, okay, just look at my hand. If I move to the left, I am stringent. I am lowering false negative probability, but increase false positive probability. If I do this, right? So it's always a trade-off. Okay. Now, what means more? Well, if the positive is death penalty, what are you gonna do? You're gonna try to make false positive as tiny as possible, right? So it's okay to let 1,000 criminals go free so that you can minimize probability that you execute an innocent person, right? So you're gonna be very, what? Very lenient, okay? If that judgment is death penalty. Now, the other judgment. What if it were a medical reading and the judgment is better screen this person for COVID? Is it deadly? No, because what's going to happen? Take him to the room and do a swab. Cost 10 baht or 100 baht. Right? Are you going to be lenient or stringent? You're going to be very stringent, right? So you're going to have a whole bunch of false positive. It's okay. Right? Because you can't afford to have false negative running around the population. Okay. So, homework number 2 is go to, well, this one's up to you. Go to Wikipedia, go to ChatGPT, go to anything you like, and tell me, describe, okay? I'm going to put down the word false, positive, false, negative, true, positive, true, negative. And based on this, I can tell you this. False positive plus false negative divide by the whole thing. That's your accuracy. Okay? But as with the problem with COVID and death penalty, you care for different things. Go to the homework is to describe 2 words. Write this down. One's called precision. And one's called recall. Yeah, that's homework in terms of this. Okay. Number 2, this is number 2.1. Number 2.2. Okay. This ROC curve is a bit hard to understand, to read, but all it is plotting that trade-off. Okay, it's plotting that trade-off. Now, the ratio of false positive and false negative, if the model is no good, okay, if the model is no good, the trade-off is always there. The trade-off is over there, always there, okay? But if the model is no good, the probability of false positive is the same thing as, you know, random, okay? So you just randomly say guilty or not guilty or something like that. Well, the way you read, okay, and this is sort of like, let's say you kind of like walking by 10 meters away. You don't even know what's on the line, but you see this picture. You see this 45-degree line, and you see the curve that looks a bit like this. Okay. Now, the reveal is that this line corresponds to a model that's completely random. Has no idea. But the model is good if it goes here. Basically, you can reduce, it's always a trade-off, like I said, between false positive and false negative. But the trade-off is less severe if you can get more true positive without getting a lot of false positive. You can get a lot of true negative without getting a lot of false negative. Okay, it's always going to be a trade-off, but this is a trade-off that's better. Okay, and here, okay, question 2.2 is, what is this axis? What is this axis in terms of, again, precision, recall, or, you know, you can go back to the true positive, false positive. Do you understand my homework? My homework is precision and recall as a definition from those false positive, false negative, true positive, true negative. Second, study about ROC. Tell me what it stands for. There's some historical reason why the names are intuitive. Okay, what is this? Okay, this curve will actually plot this thing here. There'll be precision and recall, but maybe it's not there. Maybe it's 1 minus precision or 1 over recall. What is it? Tell me. Okay, go find out. Okay, so with that, okay, come back. So stop share here. So now, back to our book. Okay, then it take drop. Okay. Well, I want you to study, but at least you already see something like, you know, there's a false positive rate, there's recall. So it's already actually in the book. But no, I want you to read from somewhere else. Okay. Yeah. Okay. Anyway. Okay. So normally that's finished. Okay. In other words, you develop the model. It tells you how well it does in terms of false positive, false negative, and all that. Right? Okay. There's a difference between model calibration and model development. A model, long story short, in terms of this, model developments, you want to get to the model that really is good. The better the model, the more this curve is kind of like fat above the 45-degree line. Okay, so this is very good. This is almost perfect. Okay, the reason it's almost perfect is because the problem is trivial. In real life, you will get your ROC line kind of like this, guys. Maybe I should show you some real life ROC line. Okay, so maybe I should go to internet. You will see that in real life, you type in randomly ROC curve. You see the picture. Yeah, there it is. Okay. See, that picture is above 45-degree line, but it's never that fat. Okay. Now, this problem is fat because it's a simple trivial problem. Okay. Anyway. So, you test. Model development gets you to good. Now, what happened is this. Let's say this is the best you can do. Well, let's say this is the best you can do. Okay. There it is. Okay. The model that's random. Oops. Can you guys see this? Okay. The model's random will have area under the curve exactly half, right? Because it's 45-degree line. The model that is good will have nearly 100%. Most model will fall somewhere in between. It'll be like this. Okay. Now, so model development is try to get discriminatory power higher. But once you stop developing the model, it's like you stop the criminal proceeding. Then it becomes a matter of judgment how much you favor one type of error over the other. Okay? If you are staying over here, that's like you are very lenient. You have low false positive rate, but you also have no true positive. Nobody goes to jail. Okay, everybody comes, everybody go home. No false positive whatsoever. This thing here would be, so at this 2 point, okay, you don't need a model, okay? At this point, at this extreme point, you don't need a model. This point, you have 0 false positive rate. You also have 0 true positive. Everybody goes home. Here, this point, you have 100% false positive rate. Okay? So everybody's not guilty. You say it's guilty, but you also have 100% true positive because everybody goes to jail. Doesn't matter if you're innocent or not, right? So from here, it's like completely 100% lenient judge. Here is 100% strict judge. But the difference is that in between, the judge is not 100% either way. The weak prosecutor will give this line for the judge. A perfect prosecutor or detective will give this line for the judge. Most of the case, this is what the judge see. Okay? And if it's a COVID problem, COVID screening, where would you be? You'd be kind of, okay? Here, right? False positive everywhere. Okay? So I might have said this up the other way around. So false positive, perfectly false positive, everybody's positive. So that's kind of like COVID. This is kind of like death penalty. Okay? Death penalty, COVID, screening. Okay? So medical screening is always like this, and then criminal proceeding is always like this. Except military court, I think you're guilty until proven innocent. But most of the time you're innocent until proven guilty. So this is, you have to explain this thing. This is a good picture. So random classifier, better, perfect classifier, okay? So in this case, perfect detective or lousy detective, okay? Now, so that's it. So development, okay? Remember I told you that I look at this performance, not just on the testing, on the training, because it's not a one-shot deal. I can keep going back until, let's say I get something very weak, I can move it until it gets better for both training and test. That's called development. But in actual use, yeah, it's up to the user. If you want to be a lenient judge or strict judge, okay, that's not up to you. Okay, that's not a technical problem. It's a social value problem. But either way, your job's done. You build a model, anybody can use it. And now anybody can use it like this. Instead of a built-in classifier, instead of a mathematical model repository, then you have something like my model. And then you can publish. In fact, you can publish on paper with code, sharing your algorithm. Okay. So let's say you go to paper, you publish and say, this is a model for discriminating happy cat from unhappy cat. Nobody's ever done this before. Everybody only identify cats and dog. I'm the first one in the world who developed a machine learning algorithm that can distinguish happy cat from unhappy cat. And for that, I'm going to publish my result on paper with code, describing my methodology with a PDF file, give the data repository of my cat picture, as well as my code in a GitHub. Okay? And you can publish it. And if that turns out to be the most like game-changing, in 5 years' time, Mathematica will put that inside the data model repository. Okay? So it'll be your name would appear here. Yeah. This would be like a super special Basai / cat happiness identifier. Okay? That's how it's done. Basically, that's how it's done. Okay? So once again, you have built-in model that's simplistic. You have not a built-in model, but kind of curated set of model. Okay, the easiest one is in the Mathematica net repository, but the more advanced or more comprehensive up to October 2024 is in paper with code. Okay, chances are in your project you don't have to use the most advanced up to October 2024. Okay, so you will find a lot of what you need in here. The reason you will not find what you need is because, again, your problem is unique. If your problem is to identify Cezanne, okay, this is Jen. If your problem is to identify caption image, you're probably not going to do a better job than what's done for you. Okay. So your project will be kind of like heavy on the data or heavy on the methodology. Okay. Now, so that's so if you're really a professional data scientist, do this, and if you are if you kind of like machine learning innovator, you would actually develop your model and publish on paper with code. Okay. Now, technically, in scientific literature, you publish in a journal. Paper with code is different. It's not peer review, so sometimes you get a lot of rubbish work. Okay, I put my work there. My work is not that great. Okay, so there's no peer review. But what's good is that anybody can replicate because there's code. That's a trade-off, because a lot of scientific journal is peer review, but if you read it, you have to believe it, because you can't get to the author's experiment. Remember, scientific experiment used to be real experiment with cats and dogs and chemistry. So you don't really want to replicate that in your backyard, right? So you just have to believe that the university is honest. They test this on mouse, they test this on rat, they test this on amoeba, and this is the result. You're not going to replicate it yourself. You don't have a lab back home, right? So the university has to be honest, the journal has to be honest, the publication has to be honest. But with things like data science, where you can literally download the algorithm and run the number yourself, right? It's like this experiment can be verified by yourself. No need to believe what's printed, because they show you how it's done, they give you the code, and they give you the data. So when you go to paper with code, Number one, if you don't believe it, you go to their code, you go to their data, you replicate it, see if you get what they claim. Once you believe it, the upside is now you own the code. No, you don't own the code, but you have the code. Now you can use it on your problem. Again, if your problem is the same one that they have done. Okay. If your problem is among these, you can use it. Okay. So your project can be now in the previous class, my emphasis is on your data, building the data. So I don't really want students to use pre-built model. I wouldn't mind. In fact, I would like if they use the data repository, but I want them to train themselves. Okay? Because this data can be like something that's similar to yours, but not quite. So you can say that my data is a little bit like this. So basically, I would prefer that you have your own data and you build it. Okay? But I recognize that every single year, the model gets more and more complicated. The way of working with built from scratch model is slowly fading away. You are most likely going to be adapting from a pre-built model. I haven't shown you how to do that yet. Okay, it's called transfer learning. Okay, so you either you build your own model, again, using this classify function or whatever, right? Just like in the textbook. You use the built-in function or use the model that's in the repository. In real life, it's somewhere in between. Okay, what do I mean by that? You have a problem identifying happy cat from sad cat. However, there happened to be a model for identifying happy human from sad human. You see what I mean? So it's close to your application, not quite. You have to do a little bit more of a transferred learning. You take the model that's there, but you add a bit more neural network of your own. Does that make sense? Does that make sense? That's called, and that's going to be how you work. But for this class, I still think that you gain a lot from working with your own data. Okay, but take inspiration from this. So if your data is based on agriculture, what I would do is, look at the example of agricultural data. If your data is based on botany, I would look at the example in botany and see how they display botany, right? So borrow the way they visualize data and analyze data. That's how you learn. Okay, this is not copying. This is learning from example. Okay, well, it is copying, but that's how you learn. You copy in this sense. Okay, it's not a knockoff. It's a learning process. So yeah, a lot of people would work in sustainability and all kind of smart city. Then you would look at things like this, like logistic. Where's logistic? Should be here somewhere. And demographic, definitely a lot of stuff. Yeah. So all this manufacturing, logistic, I think it's in here somewhere. I don't know why there's no category that's separate, but it should be. Oh, well, maybe not. Government culture. Okay. So agriculture, all these things, these are really good data. Okay. And it's very nice. There's no messiness. Okay. So you're not quite here. Okay. You're not quite here. You're kind of like here. Okay. But today, I show you what it would be like if you were here in the beginning, before the break. Okay. And after break is this. I'll give you this note just to remind you. Okay. Now, what happened in this? Okay. So you have the homework. Let me summarize again. The first is, again, go to the classify pre-built, right? And then do some example and see if you can find similar tasks in the model a net repository, neural net repository, and try for your example. your face, your picture, I don't, whatever. And like I found, the age prediction for that model is better than the one that's pre-built, that's built in. The built-in is kind of like a quick Mickey Mouse thing, right? So that's example for work number one. Number two, dig deep into the ROC. Start with the search ROC curve, okay? Or go to ChatGPT, get explanation, and then see if you can confirm that, yeah, bad model or random models like this. By the way, it can get below 45-degree line. It can get a model that's worse than random, okay? In other words, more wrong than random. You can that happens in real life, guys. I'm not kidding you. Okay, that happens. Okay. Anyway, but let's say typically you have a random model, a little bit better random, and then you have perfect model. Okay. Most of the time you have this kind of like better than random, but not perfect. And depend on whether or not you want to be a lenient judge or super strict judge, depending on the problem. Basically, it's the social cause of falseness. Is false positive more dangerous, or is false negative more dangerous, right? For death penalty, false positive is bad, right? Because you kill an innocent guy, he can't come back to life, right? All right. Whereas with COVID, false positive is no big deal. You go to another test, right? False negative is dangerous because then you're spreading the disease. Okay. So that's what you want. I want you to learn. Okay. And the book, again, you follow that, and you will be in this bracket, in this kind of like, actually, let me call it class note today. Okay. Once again, I've used up my, so next week, I think I want every one of you now to formulate very clearly what you want to do. Okay. Now, could you apply one of the data from depository and model from the repository and build a user interface? Yes, you can. And if you did a good job, you can get an A, right? But I would also prefer, okay, since the proof of concept is not whether or not you can produce a nice user interface. The proof of concept is you understand how to analyze data. And you should have the data that matters to you more than me. And if that happens to be a problem of identifying cat happiness, then you need to build the model. Now, I haven't shown you how to build a convolutional neural network type thing, but you can. It's not that difficult. Okay? So, last thing I want to put in before I forget is that here, between here and here, let's say I'm going to put something like intermediate. No, I'm not. No, that's okay. Don't worry. Basically, if you can think of this as like something that's in the book, but in your project, you're not going to do it one time, right? You're going to keep developing, testing, try different configuration and so forth. So maybe something like, let me do that. Sorry, let me do that. So let's say intermediate data scientist, like above, but you kind of like actively tweak the method. Okay. And just to give you the page, you guys remember, so this one, right? This one, I can say predictor or classify, and I can put it neural network, right? But I don't tweak the neural network. I just say neural network. If I want to tweak, I would use, let me just add it for completeness. A net chain. There it is. Okay. So instead of devising your own model, instead of using just quote unquote neural network and build me some neural network, you are actually going to specify the architecture. So it would be something like this. So chain. Okay. Maybe there's a guide, Mathematica, working with a net chain and transfer learning. Maybe that's a good one. Perform net saturated. Oh yeah, this is a good one. Yeah, I might as well give you this link because this is actually something that for those of you going on to be digital intelligence, I think it's very useful. Where was that search page? Internet. Okay. And I'll give you another one. Perform, no, not perform net surgery, transfer learning, net train. Okay. Okay, there. Okay, there you go. And let's add another thing. Let's call it machine learning tech entrepreneur and innovator. Okay, you would not do this. You would not develop your own model. You would kind of like synthesize elements of above into app. This is what you guys like to do, right? Okay. So some of you may take algorithm from here, take some kind of, Mathematica-like thing to do a prototype interface, and then, so this will be the last. This is kind of like very basai, I have to mention, okay? But yeah, you don't need that. You know that. You can also, okay. So save as, what's today? Class notes. Note S or S? No, S notes. Okay. Okay, I'll send you this and come back. So don't forget your homework should be on, is it Friday? Have you graded the student turn in all the homework? Nobody missed, right? The last time. Okay. Okay, so that's it. Next week, we will definitely start on unsupervised learning, okay, which is like another big chunk. And then for the next two class will be unsupervised learning. Okay, good. Okay, I'll see you next week on Tuesday.